Hey guys, Mr. Gran here with a challenge video on factoring. So we're going to apply some factoring strategies that you've already learned to some problems that look a little bit more challenging. Alright, so difference of quads. They kind of look like difference of squares. This one is I guess it would be a quartic, and this would be like a 6th degree, but they really follow the same pattern as a difference of squares. If we think back to difference of squares, right? X squared minus 16, what you would do with that is you'd think, okay, what is the square root of the first term and the second term? Now, you probably aren't thinking about what's the square root of the first term. You're just used to it being x plus or minus the square root of the second term, but really the square root of x squared is x, so that is why this works and becomes x minus 4 and x plus 4, because the first and the second are perfect squares. So if we kind of do the same thing for these, if we think about them the same way, this first one, both of those are perfect squares. The square root of x to the 4th is x squared, and the square root of 4 obviously is 2. And so this pattern still works, x squared minus 2 and x squared plus 2. If you want to pause and do the next one, otherwise, it's really the same thing, right? When you take the square root of x to the 6th, you're dividing the exponent in half, and that is x cubed. So this is x cubed minus 6 and x cubed. That should be a cubed plus 6, like that. Not so tough. Ooh, but what about these? Quartic trinomials and an 8th degree trinomial. So this is another one where it looks a lot like something that you've factored before. It just is a little bit different because the exponents are too big. Now, one thing that's really important to notice with these, the exponent here is twice as big as the exponent here. Exponent here is twice as big as the exponent here. That's the real pattern that we're looking for with factorable quadratics, or factorable trinomials of any kind. All right, so this would work way better if instead of x to the 4th and x squared, it was x squared and x. And I'm making them red x's for this. And you'll see why in just a second. So if this were the case, if this were the equation you were given, you guys could do that because you've already done one like that, right? So this is factorable. Now if I think about it, if I can factor this, as long as I can figure out what that red x needs to be for this to work. So what I want to think about here is I've changed from x to the 4th and x squared to red x's, where it was squared and to the 1st power. So what would this red x have to be in order for this to be true? Well, this red x would have to match that x squared. So if that red x equals x squared, then I'm allowed to do this. This is called substitution. So if I think about this, I can really just treat it, I can just kind of pretend that it's this different equation as long as this pattern kind of holds true for the whole thing. So if I check, well, if I replace this x with x squared, then it's the same thing, right? Then it's 4x squared. But what happens if I replace this red x with x squared? Well, then I get x squared squared, which is x to the 4th. So this still works. So long story longer, I can do all of this stuff as long as this red x can be the same thing and I can still get back to the original equation. All right, so anyway, how this will work, we'll factor it just like normal, except it's going to be red x's now. So we're looking at the one with the red x's. All right, so I want two numbers that would multiply to this negative 45 but add to the negative 4. That would be a minus 9 and a plus 5. Now, all I have to do to make this work now is to change these red x's from red x's back to a white x squared. like that. And now if you notice, I'm not quite done, am I? Because I've got this minus 9, this x squared minus 9 over here. That's a difference of squares, so that could continue to factor. So x plus 3, x minus 3, and then x squared plus 5. All right, if you want to pause and try the same thing with the next one, it's really the same idea. This would be really convenient if it were x squared and x. So we'll make it a red x squared plus x minus 56. So now what does the red x need to be for this to work? It needs to match this x to the fourth. So each red x in the end is going to get replaced by an x to the fourth. All right, so factoring this, two numbers that would multiply to a negative 56 but add to a positive 1 are going to be plus 8 and minus 7. And now I can just replace those red x's with x to the fourths. If you make it to calculus, you will do something very similar to this, but it will be u substitution is what it's called. And so instead of a red x, it's a u instead, but same idea. All right, give these two a try. One, just because this is a challenge video, let's approach this like a difference of squares instead of a GCF at first and see where it goes, just for the heck of it. And then another one where you can use a red x to solve that one. Okay, so our first one, if we're approaching this like a difference of squares, it's a really different looking one. The square root of x to the 8th is x to the 4th, and the square root of x to the 4th is x squared. Okay, so now I have created another difference of squares over here. Now again, we could take out the GCF, but let's do difference of squares just for the fun of it. All right, so this first one would factor to x squared minus x and x squared plus x. And then the last part that is going to stay like this for now. And now I don't think we can factor it any further except for GCF. So now each one of these has a GCF. So we'll take all of them out and we're just gonna like move them all to the front, the GCFs. So for our first one here, x squared minus x, that has a GCF of x, and what's left, I'm gonna leave it off to the side here, is x minus 1. Our middle one here has a GCF of x squared plus x is a GCF of another x, and what's left is x plus 1. And then our last one, this has a GCF of x squared. I can take x squared out of both of these, so I'll take an x squared out, and then I've got x squared plus 1. And so now to simplify this, I'm going to combine these terms, I'm going to multiply them together, so I've got one variable out in front. So x to the first, x to the first, x squared makes x to the fourth, and then x minus 1, x plus 1, x squared plus 1. And if you do GCF first, eventually you would get to this as well. It would just look, the work would look a little different. It would probably make a lot more sense to do GCF, but we'll do it that way just to have fun. Because if you're looking at this, you must think that math is fun for some reason. Okay, so the next one. Let's see, we want this to be x squared. This is way more convenient if it's x squared minus 15x plus 54, and for that to work, that red x needs to be an x cubed, and that works because x cubed squared is x to the 6th. So x cubed is our substitution. Then two numbers that multiply to positive 54 but add to a negative 15 are going to be minus 9 and minus 6. And then we just have to replace those red x's with x cubes. All right, I hope that this made some sense. We'll continue with some more difficult challenge problems that'll involve this type of factoring in some of the future lessons when we get into rational equations. But hopefully if you're thinking about pre-calculus next year, you gave this a look, and don't feel like you can't email me with any questions that you have regarding this.